Imagine you are building a LEGO tower one brick at a time. The principle of optimality says that if you want the best, tallest, strongest, or prettiest tower in the end, every partial tower you build along the way must also be the best possible tower for its height. In other words, you never need to keep a tower that looks good enough now if it will block you from making the absolute best tower later. This idea is like a story where each chapter must be the best version of that chapter, because the whole book's quality depends on the quality of each chapter. Formal statement: let P be a problem that can be broken into sub-problems. If an optimal solution S star to P contains a sub-solution S prime that solves a sub-problem P prime, then S prime must itself be optimal for P prime. Proof sketch: assume the opposite dash that S prime is not optimal for P prime. Then there exists another solution S hat prime that is better for P prime. Replacing S prime with S hat prime in S star would give a better solution for the whole problem, contradicting the assumption that S star is optimal. Hence, every piece of an optimal solution must be optimal on its own dash. This is called optimal substructure. A state is a snapshot of everything we need to know to continue solving the problem. Think of it as a picture of the game board at a certain moment. A decision choice is a move we can make from that picture. For example, in a puzzle where you have to collect coins on a line, a state could be how many coins have we already taken, and which position we stand on, IC. The decision choices might be step left or step right. By clearly defining the state variables, we know exactly what to store and what to look up later. Explanation: to turn the optimal substructure idea into a formula, we write a recurrence relation. Suppose we have a state f of I that means best value we can get starting from position I. If from I we can move to I plus 1 or I plus 2, the recurrence is f of I equals max of value of I plus f of I plus 1, and value of I plus f of I plus 2. The formula says to be optimal at I look at each possible. Next move, add the reward we get now, and then use the already computed optimal value for the next state. This equation captures exactly how the best solution builds on the best smaller solutions. In a backpack knapsack problem, the recurrence looks like k of I, w equals max of k of I minus 1, w, and value I plus k of I minus 1, w minus weight I, where k of I, w is the best total value using the first I items with a weight limit w. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. There are two ways to store the results of subproblems. Memoization: top-down, start with the original problem and call the function recursively. Every time we compute a state, we write the answer into a table. If we later need the same state, we simply read it instead of recomputing. It is like writing down the answer on a cheat sheet the first time you figure it out. Bottom-up DP tabulation: fill the table in an order where all needed smaller states are already known. We begin with the simplest states, often the base cases, and iterate until we reach the big state we want. This is similar to building a Lego tower from the ground up, layer by layer. Both methods give the same final answer, but memoization can be easier to code when the recursion is natural, while bottom-up often uses less call stack memory and can be faster because it avoids function call overhead. When we count how long a DP algorithm takes, we look at how many different states we fill and how much work we do for each. If there are n positions and each position has k possible choices, the time is usually O of n times k. The space needed is the size of the table, O of n for a simple one-dimensional DP, or O of n times W for a two-dimensional knapsack table where W is the weight limit. Trade-off tip: if we only need the previous row to compute the current row, as in many shortest path or coin change problems, we can keep just 2 rows and drop the rest, cutting space from O of n times W to O of W. The key is to understand which part of the table is still needed later, and which can be discarded. In memoization, the call stack also uses space proportional to the depth of recursion. Usually O of n bottom-up eliminates this stack, but may need the full table unless we apply the row reduction trick. Shortest path, for example Dijkstra's algorithm, the best path from A to C that goes through B must contain the best path from A to B. If you already know the shortest distance to B, you can extend it by the edge B to C to get a candidate for A to C. Dist V equals min over uv and E of dist U plus weight uv. Knapsack, as shown earlier, the optimal set of items for a capacity W either does not use the current item, giving K of I-1, W, or uses it, giving value I plus K of I-1, W minus weight I. The choice that gives the larger value is the optimal one. Both examples follow the principle. The global optimum is built from optimal solutions of smaller sub-problems. Explanation: not every problem can be broken this way. Counterexample: longest increasing subsequence with a restriction on the number of swaps. Dash an optimal solution for the whole sequence might contain a subsequence that is not optimal for its own prefix, because you may need to keep a slightly worse prefix to allow a much better overall result later. Another classic failure is the traveling salesperson problem, TSP. The shortest tour that visits cities 1 to 4 does not necessarily contain the shortest tour that visits cities 1 to 3, because the order of visiting matters globally. These cases lack optimal substructure, so DP will not give correct answers. The lesson: before applying DP, always check that any optimal solution can be split into optimal pieces. Otherwise, you need a different algorithmic tool.